All right, good morning, everyone. So, today we're going to start the next section. So, basically, section 3 of our 5-section course, essentially. So, we've been talking about what we call electrostatics. So, electrostatics are electric fields, potentials, and things that are created by stationary charges, i.e., statics. But now we're going to start moving away from that and start talking about electrodynamics, which is now things are going to start to move. So, life will be great. So now we're going to have other effects and things that we're actually going to start talking about, which will lead us primarily into things like circuits. So that's primarily what we're going to be talking about during this third section here, which will then bring us to magnetic fields and then bring us to light and all that kind of good stuff after that. So the first thing to note is that now we're going to be looking at electrodynamics, which before what we said was that the electric field inside of a conductor had to be equal to 0. But that was only true in electrostatics. So before we said, but here was my conductor, we said our electric field had to be 0 everywhere inside of the conductor. This is technically only true in electrostatics, not necessarily in electrodynamics, because now we're going to be causing charges to move, which means that we have to put an electric field inside of there to cause an acceleration to cause them basically to move. So difference between the two. So before we move on, let me kind of give you a picture of what we're going to be talking about in this chapter so that you can have a kind of a mental picture of what we're going to be doing. And then when we actually talk about these pieces, you can kind of visualize what's going on and then think about these things as we move forward. So first things first is we're going to be looking at batteries. So the point of a battery is basically to supply a constant potential difference across some sort of circuit. So the battery then would supply a constant potential difference, which would then create an electric field. And that electric field would then create a force onto charged particles and then cause them to start to move. So here what I have is, here's the battery. This is our constant potential difference. And then here we have wires. So for the purposes of this class, wires are going to be zero resistant objects. But as you guys saw in lab, that's not quite 100% reality. So everything pretty much has resistance. This is the superconductor. So they do have a small amount of resistance, but for our purposes, they're going to be zero resistance. And then basically what's going to happen is during the wires, they're going to feel a constant acceleration due to the fact that, as we talked about before, the electric field is equal to the force per unit charge, which means the force then is equal to the charge times the electric field. So again, the point of the battery is to create this constant potential difference, which then creates an electric field, which then causes these charged particles to accelerate. Now, what will happen then is as they accelerate through the wire, they're going to go into some sort of electrical element, which in most cases is going to be a resistor. So basically when you turn on your electrical stove, or you turn on a light with a light bulb, or your hair dryer or something like that, all of these things are typically just some sort of resistor. So what happens then is inside of the resistor is made up of atoms. So the electrons are trying to accelerate past these particular atoms. But since these have a lot of atoms which are being distributed throughout the entire resistor, what happens is these electrons are constantly making elastic collisions with the atoms inside of the resistor, or whatever this resistor element is. So as these particles are trying to move through, they're constantly creating or undergoing elastic collisions, which is then imparting part of their kinetic energy onto the atoms inside of the resistor, which causes the resistor then to start to vibrate or oscillate faster. So then each one of these electrons on the inside is constantly speeding up, slowing down, speeding up, slowing down, speeding up, and slowing down, which causes the electrons then to move at a constant overall rate across the resistor. And that constant rate is then related to what we call the current. So the atoms inside of this resistor then causes the current to slow down, causes them to not accelerate anymore, but actually to move at constant speed. Now, every time I then make elastic collisions, again, these guys start to oscillate more and more and more and more rapidly. And remember from your kinetic theory from last semester, kinetic theory says that the average kinetic energy is related to the temperature. So as I'm imparting more and more and more and more velocity or kinetic energy onto these atoms, causing them to vibrate more, the temperature of this thing starts to increase more and more and more. which means then that the work that's being done to impart the kinetic energy onto these atoms then gets dissipated as thermal energy. So the more I start to increase the acceleration of these guys, the more energy I then impart onto the atoms, which then causes more energy to be lost by conservation of energy due to thermal energy. So as I increase the voltage of the battery, then I then increase the amount of acceleration, which then increases the amount of energy which is then being imparted onto my atoms, which then causes them to oscillate more and more and more and more, which then causes it to heat up more and more and more and more. So this is what causes a wire to actually heat up, is the higher the potential, the more energy is being imparted onto the wire, which then causes it to actually heat up, which then loses energy due to thermal energy. So then what happens is then the atoms or the electrons then eventually go back into the battery. And then inside of the battery, there are little angels which then carry the electrons from one side to the other side. It's just a joke. But anyways, what happens then is the constant potential difference on the inside of the battery then causes the electrons to move uphill, which is kind of the same idea of what? So initially, when they move inside the battery, my electrons are sitting down here. The point of the battery then is to bring them up to a higher potential difference. So that way I can use it to fall, use that kinetic energy to then do work, causing the electrons to then cause a closed circuit to then have power going through the circuit. So this is basically our mental picture that we're going to be looking at. So the point of the battery is to create a constant potential difference, which then creates an electric field. That electric field then accelerates the electrons through the wire. They then impart themselves onto a resistor. Then the electrons make elastic collisions with the atoms inside of the resistor, causing the atoms inside of the resistor to increase the kinetic energy. By conservation of energy, they then have to lose that increase of energy to thermal energy, which then causes the electrons to move at a constant rate instead of a constant acceleration. And then it goes back into the closed system. So, anybody know, out of curiosity, what the point of a circuit breaker is in your house? Not quite a surge. What do you mean by surge?
An overload.
An overload? Okay, so what's an overload? Too much current. Good. And the reason for that is that each wire has a particular grade. So you have different sizes of wire, like 18 gauge, 16 gauge, 20 gauge, 22 gauge, where each one of those has a particular amount of current which is allowed to go through it. So you use different sizes of wire inside of your house that allow a particular amount of current to go through. And then if your system overloads the amount of current, what that means is now the atoms inside of the wire are vibrating so much that the heat is going to get so great. So the thermal energy which is given off would get so great that you would actually burn down your house. So the point of the circuit breaker then is to monitor the amount of current which actually goes through each wire to make sure the temperature doesn't get too hot so that you don't burn down sections of your house. So this is the entire point. Probably a good thing. I don't want to waste all that money I spent on my house. Watch it burn down. So anyway, so this is our mental picture we're working with basically through most of this chapter, and we're going to kind of switch up at the end. So first of all, let's start talking about a battery. So what is a battery? So okay, the point of the battery is to supply a constant potential difference. So, and what's called an ideal battery, this is what the ideal battery would do. No matter what happens to the system, I would have a constant potential difference at all times. So this is what we call an ideal battery. So an ideal battery would keep the potential difference the same regardless of how much current I'm actually running through my system. Now, as you guys have actually seen in the lab, this of course is not the case. When I start actually running current through my system, the battery actually depletes. So the amount of potential difference across the battery actually reduces. So this is what we call a realistic battery. But a realistic battery is its potential difference increase as the current increases. We'll talk more about how to handle a realistic battery later, but just know this is the way that batteries actually work. So typical batteries that you'll have are, you can have this type of battery. So this is more of an old school battery. So today we use more chemical batteries as opposed to this one. But this is something that you might find, for example, in your car. This would be more like a car battery. So the way that your car battery works is it's created from a whole bunch of individual cells. So this would be one particular cell. So in the cell, you typically have two metals. So you have what's known as a cathode and an anode. And then you have it sitting inside of a acid, which is what's known as an electrolytic fluid. So basically inside of here I have an acid, and then here I simply have two pieces of metal. So I have the anode and then I have a cathode. So the cathode is the positive terminal, and then the anode is then the negative terminal. So basically what happens is what? So as I have it in the acid, one of the two metals is usually more corrosive than the other one. So basically meaning that as it sits inside of the electrolytic fluid, the acid then starts to dissolve one of the two. As it starts to dissolve, what ends up happening then is as the metal is actually being dissolved, the positive charges start falling off into the electrolytic fluid, leaving then negative charges onto the metal itself. So this is my anode, that's what's happening here. So basically here what's happening is all the positive charges are being dissolved, going into the electrolytic fluid, leaving nothing but negative charges then onto the anode itself. So my electrolytic fluid now becomes positively charged. It doesn't want to stay positively charged. So what happens in that case then is from the cathode, I start then depleting negative charges then from the cathode into the electrolytic fluid, trying to get it to neutralize, so it becomes zero charge. So my negative charges then start coming off of the cathode, leaving my cathode then positively charged. This happens typically at a constant rate. So this is why it's supplying technically a constant potential difference. So this is being dissolved at a particular rate. This is then giving off negative charges into my electrolytic fluid at a constant rate, which then creates a constant potential difference across it. So this would be like a D battery, again, a car battery, something like that. Something has an electrolytic fluid or an acid on the inside of it. Now, what happens then is when I apply a current to the system, so I put wires onto it, have it go through and then run my, say, radio or something like that, or a flashlight, this rate at which this is being dissolved and the rate at which these negative charges are going into the electrolytic fluid stay at the same rate, but now I'm causing electrons to then move through my system, but that happens at a much faster rate than what it is that these guys are being depleted, which then causes the potential difference across the battery to actually decrease. So this is why I have a realistic battery where the potential difference decreases, because now it can't hold that constant potential difference anymore because the rate at which these things are flowing into the electrolytic fluid remains constant, and it's not fast enough to keep up with the draw at which electrons are going through. So that's what causes the potential difference then across the battery to actually deplete and get smaller over time. Now what happens then is this thing will keep dissolving forever until eventually I have nothing left to dissolve. When I have nothing left to dissolve, that's when my battery dies. That's when my battery becomes a dead battery. And I can't charge it, I can't do anything. The only thing I can do at that stage is throw it out. Now this is different than what you would find, for example, in a cell phone. In a cell phone, it's typically a chemical battery. So what happens in that case is you have a membrane here in the middle. You have positively charged particles on one side, negatively charged particles on the other side. And what happens then is they both start to move through the membrane, and they start to intermingle with each other. As they start to intermingle with each other, that's when the battery starts to deplete. Until eventually, I have no positive charges on this side, no negative charges on this side. Everything is strewn throughout the entire thing. So I have no net flow of charge. I have no current. In that case, I have no more potential. My battery is dead. But when I connect it to a power source, what I do in that case then is I drive all the positive charges back to one side, all the negative charges back to the other side, create that potential difference again, and then allow the system to go through again. So yeah, so things that I would have in my cell phone, iPad, anything like that, these all have chemical batteries inside of them. Again, these are more things like car batteries or D batteries or C batteries, or et cetera. But again, this is typically the way that a battery works. So the electrolytic fluid just two different pieces of metal. One might be zinc, the other one might be copper or something like that. One of them dissolves faster. Again, the one that's being dissolved puts positive charges into the electrolytic fluid, which then pulls negative charges off of the other one to try to neutralize, which then creates that particular potential difference. But this is the point of the battery. Create a constant potential difference. Now, once I create a closed circuit on top of my battery, then I can start having charges flow through my system. As charges start to flow through the system, we can then talk about what's known as currents. So, we talked about this a little bit in the lab, but let's talk about it again. So what's current? So current now is like constant potential difference across this electrical device, which then creates a constant electric field. And then in that case, I'm going to have charges go across my electrical device. So here's my charge. My charge then is going to start to flow in the direction of the electric field thanks to this constant force. So what we define then as current is, we say, let's take a cross-sectional area of this electrical device here. And I'm simply going to count the number of charged particles which pass through this cross-sectional area in a given number of time. Let's say I have one charge passing through, second charge passing through, another passing through, etc. So in a time frame of delta t, we then have what's known as the average current is then equal to the change in charge divided by the change in time. So this is what we call current. So current then is simply the number of charges which pass through this particular cross-section in a given amount of time. This is the average current. Or for our purposes, we're going to call it the current. So this is current. As we're talking about in the lab, we'll talk about it again. This has units of coulombs. This has units of seconds. So current has units of coulombs per second, which gets a special name, which is what's known as an ampere. Capital A. So this is current. So again, current is just looking at the number of charges which pass through this thing at a given moment of time. Now, one important thing to note about currents is, thanks to Benjamin Franklin, we think currents is actually positive charges moving in the direction of the electric field. Turns out this is actually not correct. It's actually electrons moving in the opposite direction as the electric field. So for this class, and for any class dealing with circuitry, Q for us will always be positive, moving in direction . But in reality, it's actually electrons moving opposite. So Benjamin Franklin didn't know. He just knew that there were charges moving through this thing after shocking himself by holding a kite in the middle of a thunderstorm, because that sounded like a great idea. Anyways, so when he did that, he thought it was positive charges, which were then, turns out it was actually negative charges. After we talk about magnetism, we'll talk about the experiments which actually showed they're actually negative charges. It comes from what's called the Hall effect. So this is how we actually determined it was negative charges, not actually positive charges. Turns out it actually doesn't matter. The current stays the same way, regardless if they're positive charges or negative charges. But again, for this class, we're going to say that we have our potential set up across here. So this is my battery, positive side, negative side. So in this case, my electric field would point in this direction. For us, it's always going to be positive charges moving through the circuit. So we would then say that the direction of the current in this case would be in this direction. Now, other things to note about current is we're going to view current as flowing in a direction, but current actually is not a vectorial quantity. It's actually a scalar quantity. So we'll view it as moving in a direction, which makes us think that it's actually a vector, but it's not a vector, it is simply a scalar. Current is a scalar quantity, not a vectorial quantity. Which works out out pretty well, because if I had, for example, one wire attached to two other wires, where one was going in this direction and say one was going in this direction, if I had, say, an initial current coming inward in this direction, I1, and then I have two other currents going through the two other wires, so that this becomes, say, I2 and this becomes I3, the fact that this is not a vector means that I don't have to worry about the angles at which these wires are going at. The only thing I care about is conservation of charge, which says if I have charge coming in, I have to have the same amount of charge coming out. So conservation of charge says then that the current I1 then must be equal to simply the current I2 plus the current I3. So this comes from conservation of charge. All this says is that the charge coming in to this particular point, which is what we call the junction, where current gets split off and move into different directions, is simply then equal to the charge coming out plus the charge coming out. So the total charge out must be equal to the total charge in. Again, if this was a vectorial quantity, now I would have to worry about the angle at which this was at and the angle this was at, and I'd have to vector sum them together and blah, 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 and it would just kind of be not so much fun. Okay, so even though we're going to view currents as moving in a direction, again, it's not a vectorial quantity, it is simply a scalar quantity, which means it's simply a number divided by number, which gives me a number. So this is current. Again, the direction of the current flowing is in the direction of the positive charges flowing in the direction of the electric field. So now, if I have this particular circuit, and my battery here is applying a constant potential difference of V, and then I measure the current going through this particular electrical device, it turns out that if I plotted the potential versus the current, these two are linearly related to each other as long as I'm dealing with a metal. So if I increase the potential difference across the battery, so for example, if I did 1 volt and then 2 volts and then 3 volts and then 4 volts, turns out that the current also increases linearly compared to that of the potential. So as I increase potential, I increase the current. These guys increase linearly with each other, which simply says that the potential difference supplied by the battery is then directly proportional to the amount of current flowing through the system. Turns out that the constant proportionality between the two, i.e. the slope of this thing, is simply equal to what we call the resistance. So the potential difference then is equal to the current times the resistance. So the resistance then is equal to the potential difference divided by the current. So we now know this thing has units of volts divided by the units of a current, which is what we call an amp. This thing gets a special name, which is what's called an ohm. So resistors have units of ohms, which is a volt per amp. Now, again, as we talked about in lab, the only caveat to this is only true in metals. i.e. conductors. Which means that if I'm not dealing with a conductor, this doesn't work anymore. This is what's called Ohm's law, or Ohm's tremendous idea, because it only works for conductors. That's fine. So this is what we call Ohm's law. Ohm's law says that the current is directly proportional to the potential by the resistor. So let's talk about this for just a second. So what this thing says is that what? To have a current running through my system, I have to have a resistor. So this thing says if I directly connect a wire to a potential source, I technically don't have any currents. Well, actually, in that case, I would have infinite amount of currents, because if the resistance is 0, I would have to have an infinite current running through the system to make sure that the potential stays equal to a constant. So I can't have a current without a resistor. The other thing to note is that the current is not dictated by the potential, but the current is actually dictated by the resistance. As I change the resistance, I change the amount of current. So this is kind of one misconception a lot of people will have when they get struck by lightning, for example. They look at the huge potential difference that you're getting struck by and think that you're automatically going to die, which could be true. It doesn't necessarily have to be true. Because what kills you is actually the currents, not the potential. So if you had a very large potential, but you have a very large resistance, then you have a very small current, and then you're safe. You're not going to die. So currents is actually dictated by the resistance, not by the potential. Current resistance, not the potential. So again, if I have a very large potential, but I have a very large resistance, then I can have a very, very small amount of current. And for a human person, it takes about 100 amps of current running through your heart to kill you. So even if I had a very large potential, as long again as that resistance is nice and big, you're going to be fine. Might be scary. Right? So how do we actually view resistance? So we know that resistance, again, is the constant proportionality between the current running through this electrical circuit, and that's of the battery. But how can we actually understand what's happening here? So the way we can actually understand here what's happening is we do what we did in lab and basically draw. So again, inside of my electrical object, I have charges, or I have atoms. These atoms are basically everywhere inside of my electrical object. And if I connect this into a battery, apply a constant potential difference across the battery, creating the electric field through my electrical circuits. And here, what we know is that, well, here's my charged particle, charge Q, it's going to be accelerated in the direction of the electric field. So this thing is going to feel an acceleration in this direction. Now, as this thing is trying to accelerate across this particular electrical circuit, what will happen then is, this thing is going to accelerate until it makes an elastic collision with this atom. It's then going to bounce off, accelerate back in the direction in which it came from, bounce off again, accelerate with this one, accelerate with this one, accelerate with this one, this one, this one, this one, this one, this one, etc. Until eventually this thing is going to bounce around and not always be accelerated in one direction, but constantly be changing the direction of the acceleration, causing it to take a long time to move through this particular electrical circuit, and then eventually come out through the other side. So this is now going to be my charge, moving in this direction. Now, as we've talked about in the lab, best way I can kind of describe this is the same thing as when you're trying to do 80 on the Lloyd. But like this morning when I was trying to get here, there were so many cars. Most of them were driving all side by side with each other, doing about 45. Got surprised by that. I saw 45. But anyways, I was trying to do 70. I usually do 70 instead of 80. Try to be somewhat of a good boy. But anyways, I'm trying to get through the traffic, but I can speed up a little bit and slow down, speed up, slow down, speed up, slow down, speed up, slow down, speed up, slow down, which means that at one point, my instantaneous velocity might be 70, 75. Another moment, my instantaneous velocity might be 40, 45. But then if I went over the entire duration of where I started to where I finished, and I take that distance and I divide by the time, my average speed coming here was about, let's say 55 miles per hour. So even though my instantaneous velocity is constantly changing, I have an average rate which is slower than my instantaneous velocity or faster than my instantaneous velocity as I'm trying to go from point A to point B. Here, the electron is going to do the same thing. So even though the electric field is constantly trying to accelerate in this particular direction, which means at one point it's going to have a very large instantaneous velocity, but then it makes the elastic head-on collision, bounces off, which means now it has a negative velocity as it goes backward through zero velocity, etc. So eventually this thing is going to move with a constant velocity across the electrical circuits, which is what we call the drift velocity. So what happens then is the electron, even though it's trying to accelerate across, due to these constant collisions with the atoms inside of my electrical circuit, or my electrical device here, these collisions are always causing it to speed up and slow down and speed up and slow down. So it acts as if the electron is slowly making its way through my resistor at some sort of constant rates, which is what we call the drift velocity. So the next question then is, well, how do I determine what is the resistance of my resistor based off of this picture? Right? That it's constantly then making head-on collisions with the atoms, causing it to slow down and move through the circuit. So the easiest way to do this is to think about and use the movie Saw. Did we see the original movie Saw? Yes. Some of you yes. I think I saw this in the theater. That's how old I am. Anyways. So. I hate this one. Stop it. Sure. Okay, so what we're going to do is we're going to watch part of Saw here, and we're going to use, from the original Saw movie, what's known as the razor wire trap. And we'll use that as basically our motivation for determining what the resistance of this should actually look like. I'll make a correlation between these. So those of you who haven't seen the original movie Saw, so basically what happens is one of Jigsaw's many traps here has to do with razor wire, which is then strewn across a room, basically. And then this poor sap has to crawl through the razor wire to get from one side to the other side. And if he gets out in a certain amount of time, he's going to live. So there's only a small glass to do it.
I think I may know who's done this to us. Did you say? It's not someone I know personally. It's just someone I know off. Jesus Christ, tell me! Who is it? Last I heard, police still hadn't caught him. The only reason we know that is because I was a suspect. Let's start from the beginning.
So this is the razor wire trap.
This one's not fresh anymore. He's cleared this out. Victim's a 46-year-old male. Died of massive blood loss, mostly through the femoral artery. He started at the back of the cage and tunneled his way through that razor wire so fast. It's amazing he got as far as he did. Got himself so deep he found traces of stomach acid on the floor. We also found this.
Probably know that. So basically, we can view resistance then as this razor wire trap and think about it as the probability of death. So this is basically what resistance is. So resistance then is the probability that the electron is going to die. I mean, it's not going to make it from one side of my razor wire trap here to the other side. So let's kind of talk about it going. So here's my razor wire trap. So here's the razor wires. Through doing something like this. And what I have is my poor guy here, also my electron, is trying to make it from one side of the trap to the other side of the trap. So we can think about basically the properties of this trap and then use that to write out what the resistance of the wire is. Same idea. So what are some properties that the trap has? So the properties of the trap is that it has a length to it. Right? So this is some length long. It has a cross-sectional area here, so the size at which you can actually run through. And the last thing then would be what? The density of the wires. So our resistance then is basically equal then to the probability . So let's think about each one of these properties and think about how is it going to affect this probability of death? Is it going to increase it or decrease it? So let's think about the length. So first of all, if I made this trap very, very short, what's its probability of death? less likely, right? But if I increase the length, what's this probability of that then? High. It's much more likely, right? So one thing we can then say is that this thing then must be proportional then. Well, if the rate of his death, or probability of death, increases as the length increases, does that mean it's going to be directly proportional or inversely proportional to the length? Directly proportional, right? So the first thing I know is that this is then going to be directly proportional to the length. The longer I make it, the more likely it is that he's going to die. Because if it's very short, only a few inches, all he has to do is run and jump through it. He might get cut a little bit, but he's probably just going to be fine. But if I make it, say, 10 feet, 100 feet, etc., the longer I make it, his probability of death is going to go up higher. What about the area? So meaning, if I had a very small cross-sectional area like this, and I asked him to crawl through that, is his probability of death going to increase or decrease? Increase. But if I increase the size of the cross-sectional area, so it's more like this, what happens then to his probability? Decreases. So in this case, the bigger the area I make, the less likely it is that he's going to die. Right? His probability is going to go down. So does that mean it's directly proportional or inversely proportional to the area? It's the opposite, right? Because if I make the area bigger, his likelihood goes down. So in that case, it's going to be inversely proportional to the area. If I make the area bigger, his likelihood goes down. What about the density? So let's say I have a particular density of wires. So if I have a very small density of wires, is that going to make his probability go up or go down? So let's say I only have a couple wires, it's going to go down, right? But if I increase the density, so now there's basically wires everywhere, is this probability of death going to go up or go down? Up. So is it then directly or indirectly or inversely proportional to the density? Directly. Right? So I increase the density and I increase his likelihood of death. So putting all these things together, what this says then is that the resistance of a wire then, which again is equal to our probability of death, is then equal to the density, well, we don't really call it density anymore, we'll find out in just a second, times the length divided by the cross-sectional area. So this is what we call resistance. So the resistance of a wire then is equal to rho, where rho is not quite the density, but it's what's known as the resistivity. Resistivity you can kind of think of as basically density, so the density of the atoms packed inside of the wire. L, again, is the length of it. So this is simply equal to the length, and then this is equal to the cross-sectional area of the wire. So the resistance of the wire then is equal to, again, the resistivity, which for most purposes is basically the density of the atoms. Times the length divided by my cross-sectional area. Now, we know the left-hand side has units of ohms, the right-hand side has units of resistivity, whatever that is, times length divided by length squared. Well, what's length divided by length squared? 1 over length, right? So this side has units of ohms, this side has units of resistivity divided by meters. So to get the two sides to be the same, this thing has to have units of ohms times meters, so that way it cancels this meters to make ohms and ohms. So resistivity then has units of ohm meters. So this is what we call resistivity. So, again, resistivity you can basically think of as how dense are the wires or are the atoms packed inside of the wire. Turns out this object of resistivity is related to something which is called conductivity. So let's write down conductivity. So conductivity is sigma, so we have another sigma. Unfortunately, this is that guy. Anyways, so Turns out conductivity is inversely proportional to resistivity. So what's conductivity? So conductivity is a measure of how good of a conductor a metal is. So particular metals are better conductors than other metals. So for example, when you're putting wiring into your house, you have different choices. The cheapest choice is copper. Copper is an okay conductor. Electrons will flow through, but a better conductor would be gold. Gold is a much, much better conductor, but it's also much more expensive. So when you're trying to wire your house, for example, the better conductor to use would be the gold, but if you don't have enough money to do that, using copper would still be okay. It's still an okay conductor, but it's not that great. So conductivity, again, is a measure how good conductor you have. So what this is saying then is that what? To have a good conductor, you need to have a poor resistor. Or, since resistivity is 1 over conductivity, the worse of a conductor you have, the better the resistor. So resistivity then is a measure of how good of a resistor that you have, and then a better conductor is a poor resistor, and vice versa. So the better the resistor, the worse of the conductor that it is. Okay. It also turns out that resistivity here is actually a temperature-dependent quantity, which basically means that as temperature changes, the resistivity changes, which then causes the resistance to change. So what's the temperature dependence? So it turns out that for the temperature dependence, the resistivity at a given temperature is equal to the resistivity at a different temperature, which we're going to call the initial temperature, times 1 plus alpha times delta T. So this is the temperature dependence, where alpha here has units of 1 over degrees Celsius. And this thing is what's known as the thermal resistivity. So what this thing says then is as the temperature increases, then the resistance decreases. While as the temperature decreases, the resistance, say it backwards. So as the temperature increases, the resistivity increases, which means the resistance increases. As the temperature decreases, the resistivity decreases, which then decreases the resistance. Good. So let's use all this and let's do an example. So this says that we want to connect speakers to a radio at a distant point. So then says that the wires are 20 meters long, so they're 20 meters away from the radio or whatever the source is. What diameter of copper wire must you use to keep the resistance less than 0.1 ohms per wire? Then, if the current to each speaker is actually 4 amps, what is the potential difference of voltage drop across each wire? So let's draw what's happening. So here is my source, whatever this is. So this could be a radio or a TV or whatever. And then I'm going to have a wire running out to my speaker. So this is my speaker. And what it tells me is that the length of this wire here is essentially equal to 20 meters. And what I want is that the resistance across this wire is 0.1 ohms. So what I want to know then is, if I looked closer at the wire is actually going to be doing something like this, so that this thing has a diameter d across it. What I want to know then is, what diameter do I need for this 20-meter length of wire whose resistance is simply 0.1, and this thing is made out of copper. So resistivity I said, actually depends on the type of material that it is that I'm looking at. In this case, we're looking at copper. So it turns out the resistivity for copper is 1.68 times 10 to the minus 8 ohm meters. Again, if I use gold, I would have a slightly smaller number. That would decrease the size of the resistance. Or if I was using something else, I might have a smaller or bigger number. Good. So we now know that the resistance has to be equal to 0.1. We know the resistivity, in this case, that's going to be simply equal to the copper. We know the length. The only thing I want in this case is the cross-sectional area. Now in this case, the cross-sectional area is simply this. What shape is that? A circle. Good. What is the area of a circle? In terms of its radius. Area. Close, that's the circumference. Not 2 pi r. That's the circumference, the length around. It has a pi and an r in it.
4 pi r? Is that 4 pi r squared?
That would be the cross, or that would be the surface area of a sphere. We're getting closer. Drop the 4. Pi r squared. That's our. That's the area of a circle. Put that as #1 question on the next exam. What is the area of a circle?
Track of these shapes.
Good. So in this case, what we're looking for is the diameter, not the radius. So how does the diameter relate to the radius? Good, it's twice the radius, good. So in this case, we know the diameter is simply equal to twice the radius. So to replace this radius, we'd have to write the radius then is simply equal to half the diameter. So this is then going to be equal to pi times half the diameter squared, which is the same thing as pi times the diameter squared divided by 4. So this is our area. Good. Let's plug that in. So this thing becomes now 4 times the resistivity times the length divided by pi times the diameter squared. Okay. I'm just going to solve directly for the diameter. Okay with the shenanigans I pull? Okay. So here we want the diameter, so I'm going to multiply both sides by diameter squared and divide both sides by the radius. So put the radius down here. And finally, I want the diameter, not the diameter squared, so I'm just going to take a square root. So this is my diameter then is equal to the square root of broken chalk. 4 times the resistivity of the copper times the length divided by pi times the resistance. So this is my diameter. Okay. So let's use this. Let's plug in our numbers. So this says then that our diameter is equal to the square root of 4 times 1.68 times 10 to the minus 8 times the length, which is 20, divided by pi, which is pi, 3.14, times the resistance, which is 0.1. Look at my numbers. What I find in this case then is works out to be about 2.02 millimeters. So notice the way it's written now is the diameter would give it to me in meters, and then I'm just dividing by 1,000 what it is in millimeters. In case you multiply it out by yourself. So if you multiply it out by yourself, you can get 0.00202 meters, which I then put into millimeters. Good. So that's part A. So part B then says, okay, so if we now have these 0.1 ohm wires and we apply 4 amps worth of current to it, what's the potential drop? Well, Ohm's law tells us that the potential drop is simply equal to the resistance times the current. In this case, we know our current is 4 amps. We know the resistance is 0.1 ohms, which is then 0.4 ohms. So what happens then is The potential difference between this point and this point would then be measured to be 0.4. So this is the potential drop according to Ohm's law. Right?
You use that R equals the potential difference over 8, right, which was the amps, and then just
Yeah, so I
apply those.
use, right. So R is equal to V over I, or V is equal to I. Yeah, yeah, same thing. So, all right, so let's go back to our picture. So yeah, what we have going on is the battery supplying a constant potential difference, which is then causing then the electrons to accelerate, causing them to go through then the electrical circuits, in this case, which is our resistor elements, causing them to now make collisions with the atoms, causing the atoms to vibrate. The more that they vibrate, the energy it is that they're going to lose. So we now want to know is what is the amount of energy which is being lost? So how much energy is being radiated away by this particular electrical circuits? Now, there's different forms at which this energy is radiated off. Most of it is going to be as thermal energy. Some of it will be radiation energy, i.e. light. So for example, if my resistor here was a light bulb, the point of that is basically give off light. So all my thermal energy is basically given off as radiation or radiation energy. I'm talking about my electrical circuits or my electrical elements could be my stovetop. If I had electric elements on there, again, that thing's going to glow red when it's hot enough. So in that case, it's giving off some of the thermal energy as radiation. But for most electrical devices, most of the energy is going to be given off as thermal energy. So in this case, again, what I want to know is what is the rate that thermal energy is lost by my electrical elements. How much energy is being lost, or it's the rate at which this energy is being lost. So basically, what conservation of energy says then is that what? The rate at which energy is being lost, so the power which is being lost, must be equal to the power which is being supplied. So this is what conservation of energy tells me. So conservation of energy says that initially if this thing had a particular energy, and I start applying more energy to my system, well, it has to lose that energy because it has to maintain the same amount of energy at all times. So the rate at which energy is being lost must then be equal to the rate at which energy is being supplied. Now remember power. Remember what power is? Power, by its definition. It's the rate of energy. So that means that power then is the same thing as work per unit time. So in this case, this is then the work lost per time, which is then equal to the work which is being supplied per time. So let's think about what's actually happening here. So what happens is, so here is my electrical circuits, or my electrical elements, I have in here. This thing then has a potential difference across its. So now what I'm doing is I'm trying to take a amount of current or amount of charge and then carry it from one side of this thing to the other side. So basically I want to take this amount of charge delta Q, bring it from this side and then deposit it over this side. So basically what I want to do is I want to carry this amount of current or this amount of charge delta Q across this particular electrical element, which is being held at a constant potential difference of V. So that means that the work required to move this guy from here to here is simply equal to, so the work supplied then equal to the potential energy. What's happening is, to move it from one side to the other side, I have to have a change in potential energy to go from one point to the other point. From last test, what we know is that the potential energy is simply equal to the charge times the potential difference. In this case, this is equal to the charge that I'm trying to move down to Q times the potential difference that this thing is held at. So the work supplied in this case then is simply equal to the amount of charge I want to move across this given potential difference. Right with us? So let's put this in here. So that means then that my power loss, which is equal to the work per unit time, is then equal to the change in charge divided by the change in time, times then the amount of potential which is across this electrical element. Towards the beginning of the class, we said that the change in charge with respect to time is known as what? Change in charge with respect to time. Change in charge or change in time. What is it? Current. So this is just the current. And simply equal to the current time. So look, so this thing says then that the power, or the rate at which energy is being supplied to an electrical element, which is equal to the power lost, or the rate at which energy is being lost, is simply then equal to current times the potential. So this is the power which is being lost. Now this one here that we just wrote down is good for any electrical device. It's good for any electrical elements. Doesn't matter what it is. This is true. If I'm dealing specifically with a resistor, we can use Ohm's law to rewrite the potential as equal to the current times the resistance. So let's do that. So in this case, I can write this as the current times the resistance via Ohm's law. So that this thing then is equal to the current squared times the resistance. So this is true for a resistor. Or I can also use Ohm's law to rewrite the current as being what? The potential divided by the resistance. So at the same time, I could also rewrite this then as the potential divided by the resistance times the potential. So in this case, I'm just rewriting the first one so that this thing instead becomes the potential squared divided by the resistance. This is also technically only true for a resistor. So this says then, again, the amount of power which is being delivered, which by conservation of energy is equal to the power which is being lost, is either equal to the current times the potential, the current squared times the resistance, or the potential squared divided by the resistance. Any one of these three is fine. Where specifically, the second two are talking about a resistor, and resistor only, where the first one is talking about any elements, any electrical element that we have. So the second two only apply for resistors. The first one applies for resistors, capacitors, whatever the thing is. This is true for all, even the battery. This would also be true for the battery, the power which is being supplied by the battery. So this is true for all of them. So okay, what this thing says then is what? The more current I have running through my circuit, the more energy I'm going to lose, which means the more thermal energy I'm going to lose, which means the hotter the object is going to become, which again goes back to what we talked about in the beginning. Why do we have a circuit breaker in our house? So the more current you have running through a particular wire, the hotter this thing is going to be, which means eventually you can burn down your house if you don't have something to kill all that current to then get rid of all of that thermal energy which is being lost. This one then says, well, if I increase the potential, you also increase the amount of power which is being lost. So if I increase this with a given amount of resistance, then I also increase the power loss. Okay. let's use this and let's do an example. So this says that in a lightning strike, there's of course a lot of variation. It depends on particular situations, but a typical event of a lightning strike or lightning bolt is that it has an energy transfer of 10 to the 9th joules across a potential difference around 5 times 10 to the 7th volts during the time frame of about 2 or 0.2 seconds. So let's draw our picture. So here is my cloud. Here then is the ground. Grass on the ground. Grass. So basically what it's saying is, what happens then is what? The cloud ground system basically acts as a parallel plate capacitor. This is what happens. So what ends up happening is that what? The ground, as we talked about, I think in lab, but if we did not, tell me this later, basically acts as a gigantic reservoir of negative charge. So inside of the ground basically acts as my negative plate. The cloud basically becomes positively charged. And this sets up basically a parallel plate capacitor. And what we're told here is that the potential difference across my parallel plate capacitor, in this case, is about 5 times 10 to the 7th volts. So this is my potential difference across my parallel plate capacitor. Eventually, what happens is what? The potential difference between the cloud and the ground of my parallel plate capacitor exceeds the breakdown potential of air, which then causes the air to ionize while simultaneously I want to discharge my system. So what ends up happening is the cloud pulls electrons out of the ground up into itself to then neutralize the cloud. Which means, interesting enough, and a lightning bolt doesn't strike from top to bottom, it actually strikes from bottom to top. This is what a lightning bolt actually does, because the electrons are pulled out of the ground, which means they actually run up through your feet up to the sky instead of going in the opposite direction. This is actually the way that works. So, when this happens, a lightning bolt strikes. Oh, here's my lightning bolt. I don't know if that looks like a lightning bolt. Anyways, that's my lightning bolt. And then what it tells me then is that I have a transfer of energy between the cloud and the ground, which is about 10 to the 9th joules. So in this case, the potential energy is about 10 to the 9th joules. And the time frame in which this actually happens is 0.2 seconds. So using these numbers, it then wants us to estimate the total amount of charge transferred between the ground and the cloud. B, the current in the lightning bolts, given the fact that we have a charge which is brought from one point to the other point in a time frame, so that gives us the charge. And then finally, the average power delivered over this time frame. So let's talk about all these things. So first off, since this acts as a parallel plate capacitor for A, we know that the total charge then is simply equal then to what? So this would be
Neutral energy.
well, we don't know the capacitance. There's a different way we do this. Let's go back a little bit. So we know the potential energy is equal to the charge times the potential difference. Let's do it that way. Something we just talked about. Good. So in this case, we then know that the total charge is going to be equal to the potential energy divided by the voltage. So in this case, this is going to be what? 10 to the 9th joules divided by 5 times 10 to the 7th volts, which is equal to the total charge. So this would cancel with this, which would make that 2. This then becomes a half. So this is actually then 1/2 times 10 to the 2. That's Coulomb. So this is about 50%. Oh, 1/5. No. So this is about 20 coulombs. Okay. So I got about 20 coulombs with the charge, which is then brought through this lightning bolt.
Were you getting the one fit? I just plugged it in, it's 2 times 10 to the second.
Oh, 20.
Oh, yeah. You're just doing it in a different way. Okay.
I like fractions. Okay, sure. Everyone's okay? Okay. So part B then says, okay, what's the current? Well, we know the current is simply equal to the charge divided by the time. So in this case, we know there are what? 20 coulombs. The time frame is 0.2 seconds. So this is going to be equal to 20 coulombs divided by 0.2 seconds, which is then equal to 100 amps. So this is the average current carried in the light bulb. Lightning bolt, not light bulb. Can't see it here. Finally, for part C, wants to know what's the average power. So for part C, we know that the average power, generated power loss, is either equal to the current times the potential, or we can always write this then as what? The potential energy divided by the change in time. Either one of these is sufficient. But we just learned the first one, so let's just do the first one. So this is now going to be equal to 20 coulomb, or sorry, 100 amps times then our potential difference, which is 5 times 10 to the 7th volts, which is 5 times 10 to the 9th watts. 5 times 10 to the 9th is, anybody know what that is? A lot of zeros, that's true. That's what we call a giga. So this one says that the average power, the power loss or the power supply is then 5 gigawatts. So this is our power. And as Josh said to me, what was it, last week? From anybody ever see Back to the Future? Talk about the amount of energy that he needs to travel back in time. And Doc Brown starts freaking out. What was the actual number? 1.21 gigawatts. So this would supersede that. So this would be 5 gigawatts. So this is why they actually had to get the car struck by lightning to get enough energy, because the average lightning bolt should carry about 5 gigawatts, where they needed 1.21 gigawatts to be able to travel back in time. Okay. So we're going to stop here for today, and then tomorrow we'll start picking up with the next part of this chapter, which has to do with what's known as alternating currents. So right now we're dealing with what's known as direct currents, but tomorrow we'll start dealing with alternating currents. So currents would actually change its directions over time. So start talking about that tomorrow. Okay. All right, so I'll see you in about 50 minutes for lab. Only for $5. No. Let me figure out how to turn this thing off first.